It all begins from a single origin, a unique point in space and time. This is the spark of innovation that fuels your most amazing breakthroughs. It's a passion for discovery that unveiled the genesis of all that exists in the universe. Today, the power of AI helps computers achieve superhuman capabilities in image recognition, analyzing in 1 month what used to take 10 years. Everyday devices translate even the most complex languages from voice into text and images into words, helping the visually impaired recognize an old friend or letting a blind woman read to her child for the first time. Autonomous vehicles give us the freedom to reimagine our city streets and travel where there are no streets at all to help the lost find their way home. We see robots teach themselves to perform simple tasks. We even watch in awe as they take their first steps. And today, a 2,500-year-old game meets its match as a computer competes with one of the greatest human champions of all time, and wins. This is the collective imagination, fueled by forward-looking technologies, and the beginning of your most amazing discoveries yet to come. The Big Bang of artificial intelligence is yet to come, its echo still a shimmering promise on the event horizon. While powerful algorithms waltz through tasks once deemed strictly human, a true singularity, a moment of explosive, transformative intelligence, remains just beyond our grasp. Yet, the tremors are undeniable: neural networks sprouting sentience, machines mimicking creativity, the blurring lines between human and machine. This isn't a sudden explosion, but a slow burn, a cosmic crescendo waiting to unleash its full potential, reshaping our world in ways we can only dimly imagine. The question isn't when, but how will this Big Bang of AI unfold, and are we ready to dance in its dazzling supernova?
Google Trends offers a bird's-eye view of public interest, showing how often specific terms are searched for over time. Comparing machine learning and deep learning for Google Trends reveals a curious dance of popularity. Machine learning holds the longer-term spotlight, steadily gaining interest over years. This reflects its broader appeal and fundamental role in powering many familiar technologies. Deep learning, a more specialized subset of machine learning, shines brightly in recent years. Its meteoric rise signifies its growing impact and the public's increasing awareness of its power in areas like image recognition and artificial intelligence.
The CEO of Google, Sundar Pichai, says machine learning is a core transformative way by which we are rethinking everything we are doing. Overall, Sundar Pichai portrays machine learning as a powerful force for good, capable of driving innovation and progress in various sectors. However, he also acknowledges the challenges and ethical considerations involved in its development and use.
Imagine a machine that not only performs tasks, but learns and adapts like a human mind. That's the essence of artificial intelligence, AI. It encompasses techniques like machine learning and deep learning, enabling machines to analyze data, recognize patterns, and make decisions without explicit programming. From self-driving cars to medical diagnosis, AI is transforming the world, blurring the lines between human and machine intelligence. It's a thrilling new chapter in technology, pushing boundaries and holding untold potential for both progress and challenge. Machine learning holds the longer-term spotlight, steadily gaining interest over years. This reflects its broader appeal and fundamental role in powering many familiar technologies. Deep learning, a more specialized subset of machine learning, shines brightly in recent years. Its meteoric rise signifies its growing impact and the public's increasing awareness of its power in areas like image recognition and artificial intelligence.
There are 3 types of machine learning: supervised, labeled data guides the model towards specific outputs, example, image classification; unsupervised. The model discovers patterns and relationships in unlabeled data. Example, customer segmentation. Reinforcement. The model learns through trial and error, maximizing rewards in an environment. Example, playing games. There are 4 fundamental concepts in machine learning, each tackling different problems. Number 1, classification. Imagine sorting fruits based on color. Classification tasks involve assigning data points to predefined categories. Think spam filters classifying emails as spam or not spam, or image recognition algorithms identifying objects and pictures. Number 2, regression. Picture predicting house prices based on size and location. Regression tasks find relationships between variables to predict continuous values. Examples include forecasting stock prices, understanding the impact of medication on blood pressure, or estimating travel time based on traffic conditions. Number 3, clustering. Think grouping customers with similar spending habits. Clustering tasks group data points based on their similarities without predefined categories. This helps discover hidden patterns in data, like segmenting customers into high spenders and budget-conscious shoppers. Number 4, anomaly detection. Imagine spotting a fraudulent transaction among real ones. Anomaly detection identifies data points that deviate significantly from the norm. This is crucial for detecting fraud, cyber attacks, or system failures before they cause damage.
Deep learning takes machine learning a step further, mimicking the human brain with multi-layered neural networks. Think of it as stacking learning machines to create a complex web. These networks devour data, extracting increasingly intricate patterns, like recognizing a specific dog breed in a crowded photo or translating languages with human-like fluency. Deep learning excels at tasks involving massive data sets and complex relationships, pushing the boundaries of what computers can do.
The architecture of deep learning revolves around artificial neural networks, HANs, intricate webs of interconnected nodes mimicking the human brain. Imagine layers of these nodes stacked upon each other, processing information in stages. Each layer extracts increasingly complex features from the data, ultimately generating the desired output. Key components of deep learning include input layer, receives raw data like images or text. Hidden layers, extract progressively higher level features in each layer. These layers, the heart of deep learning, employ various activation functions and learning algorithms to refine the data representation. Output layer produces the final result, be it a classification, prediction, or translation. Deep learning may seem complex, but it's built on simple principles: data flow, feature extraction, and continuous optimization. This iterative process unlocks the power of multi-layered networks to tackle previously impossible tasks. Remember, this is a simplified explanation. Diving deeper into specific algorithms and mathematical details requires a dedicated journey into the fascinating world of deep learning.
The relationship between deep learning and feature engineering is a fascinating interplay of automation and human expertise. They are not rivals, but rather partners in the quest for optimal machine learning performance. Deep learning automates feature extraction, learning complex features directly from raw data like images or text. Its strength lies in handling massive data sets and discovering intricate patterns that might elude human intuition. Think of it as a black box that extracts insightful features without explicit instructions. Feature engineering, on the other hand, applies human domain knowledge and experience to craft specific features from raw data. This involves careful selection, transformation, and combination of data points to create features that are more interpretable and relevant to the problem at hand. Imagine a seasoned detective analyzing evidence clues to build a detailed case, not just relying on raw footage. From the virtual assistants in our phones to disease diagnostics, we can see deep learning everywhere. Here, we will cover the 3 most popular and progressive applications of deep learning. They are computer vision, natural language processing, audio signal processing.
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called.
He's using it to explore the mysterious problem of how the brain learns.
This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a beetle, the computer looks at facial features and hair outline and takes longer to learn what it's told by Dr. Taylor. Andrew Cruikshank's wig also causes a little heart-searching.
After training on lots of examples, it's given new faces it has never seen and is able to successfully distinguish male from female. It has learned. While promising, this approach to machine intelligence virtually died out.
The first three events show when some of the techniques that are used today were invented. At the time, these techniques were unable to be used for real-world applications. This was largely because computing power was hard to come by, and some of the details that make these techniques effective were yet to be discovered. An interesting point to keep in mind is that these technologies are not new ideas, but applying them effectively to real-world problems is relatively new. The first three events show when some of the techniques that are used today were invented. At the time, these techniques were unable to be used for real-world applications. This was largely because computing power was hard to come by, and some of the details that make these techniques effective were yet to be discovered. An interesting point to keep in mind is that these technologies are not new ideas, but applying them effectively to real-world problems is relatively new.
First, what are algorithms and how can they be used to facilitate financial services? Algorithms are computer programs that slice and dice fundamental pieces of information to aggregate or consolidate it. Generally, in the context of fintech, algorithms are used in what is called artificial intelligence, AI, and utilize big data, BD. Algorithms use databases containing characteristics and transactions of billions of economic agents to derive patterns to predict behavior and prices and mimic human decisions. They can identify potential new clients or customers that may be interested in various financial products, or if they are existing clients or customers, to identify who may present higher risks or returns for the financial supplier. For instance, algorithms, including data from cell phone usage and contacts, internet searches, financial transactions, and ownership records, are being used by fintech firms to see which people may be potential low-risk borrowers or may be interested in various savings products. They can dig deep to see which types of products are of interest, perhaps a home mortgage loan, a small business loan, a basic savings account for a child's schooling costs, or a more sophisticated retirement fund. A product called robo-advisors is an automated system used by some banks and asset managers to provide portfolio investment advice to potential clients that input certain types of information. Alternatively, in more sophisticated settings, like automated trading platforms, algorithms could be used to see who gets to trade first when the price of a stock or bond is within the range provided by an investor's order.
Deep learning is a form of machine learning. It is known as deep learning because it contains many layers of neurons. A neuron within a deep learning network is similar to a neuron of the human brain. Another name for deep learning is artificial neural networks. A deep learning model is trained by setting an objective for what the model wants to learn. then optimizing the model's parameters to improve performance. This is different to traditional machine learning, which requires manual crafting and selecting of features, properties of data that the algorithm should examine, which takes time and is not always effective.
Imagine a neural network as a kind of black box, which takes one or multiple inputs, like the sensors of a self-driving car, processing them into one or multiple outputs, like the controls for that car. The neural network itself consists of many small units called neurons. These neurons are grouped into several layers. Neurons of one layer interact with the neurons of the next layer through weighted connections, which really are just connections with a real valued number attached to them. A neuron takes the value of a connected neuron and multiplies it with their connection's weight. The sum of all connected neurons and the neuron's bias value is then put into a so-called activation function, which simply mathematically transforms the value, before it finally can be passed on to the next neuron. This way the inputs are propagated through the whole network. That's pretty much all the network does. But the real deal behind neural networks is to find the right weights in order to get the right results. This can be done through a wide range of techniques, such as machine learning.
What is an activation function and why use them? The activation function decides whether a neuron should be activated or not by calculating the weighted sum and further adding bias to it. The purpose of the activation function is to introduce nonlinearity into the output of a neuron. We know the neural network has neurons that work in correspondence with weight, bias, and their respective activation function. In a neural network, we would update the weights and biases of the neurons on the basis of the error at the output. This process is known as backpropagation. Activation functions make the backpropagation possible since the gradients are supplied along with the error to update the weights and biases.
Why do we need nonlinear activation function? A neural network without an activation function is essentially just a linear regression model. The activation function does the nonlinear transformation to the input, making it capable to learn and perform more complex tasks. The neural network learns by generating an error signal that measures the difference between the predictions of the network and the desired values, and then using this error signal to change the weights or parameters so that predictions get more accurate. What is gradient descent? Gradient descent is an optimization algorithm which is commonly used to train machine learning models and neural networks. Training data helps these models learn over time, and the cost function within gradient descent specifically acts as a barometer, gauging its accuracy with each iteration of parameter updates. Until the function is close to or equal to 0, the model will continue to adjust its parameters to yield the smallest possible error.
What are deep autoencoders? A deep autoencoder is composed of two symmetrical deep belief networks that typically have 4 or 5 shallow layers representing the encoding half of the net, and second set of 4 or 5 layers that make up the decoding half. The layers are restricted Boltzmann machines, the building blocks of deep belief networks, with several peculiarities that we'll discuss below. Here's a simplified schema of a deep autoencoder structure, which we'll explain below. Processing the benchmark data set. A deep autoencoder would use binary transformations after each RBM. Deep autoencoders can also be used for other types of data sets with real-valued data, on which you would use Gaussian rectified transformations for the RBMs instead.
One of the most popular deep neural networks is convolutional neural networks, also known as CNN or ConvNet, in deep learning, especially when it comes to computer vision applications. What is CNN? In deep learning, a convolutional neural network, CNN/ConvNet, is a class of deep neural networks most commonly applied to analyze visual imagery. Now when we think of a neural network, we think about matrix multiplications, but that is not the case with ConvNet. It uses a special technique called convolution. Now in mathematics, convolution is a mathematical operation on two functions that produces a third function that expresses how the shape of one is modified by the other.
What is recurrent neural network? RNN. Recurrent neural network (RNN) is a type of neural network where the output from the previous step is fed as input to the current step. In traditional neural networks, all the inputs and outputs are independent of each other. Still, in cases when it is required to predict the next word of a sentence, the previous words are required and hence there is a need to remember the previous words. Thus RNN came into existence, which solved this issue with the help of a hidden layer. The main and most important feature of RNN is its hidden state, which remembers some information about a sequence. The state is also referred to as memory state since it remembers the previous input to the network. It uses the same parameters for each input, as it performs the same task on all the inputs or hidden layers to produce the output. This reduces the complexity of parameters, unlike other neural networks.
Generative adversarial networks, or GANs for short, are an approach to generative modeling using deep learning methods, such as convolutional neural networks. Generative modeling is an unsupervised learning task in machine learning that involves automatically discovering and learning the regularities or patterns in input data in such a way that the model can be used to generate or output new examples that plausibly could have been drawn from the original dataset.
What is differential neural network? The differentiable neural computer is a neural network which takes advantage of memory augmentation and, at the same time, the attention mechanism. A machine learning model called a differentiable neural computer, DNC, which consists of a neural network that can read from and write to an external memory matrix, analogous to the random access memory in a conventional computer.
What is word embedding in NLP? It is an important term that is used for representing words for text analysis in the form of real-valued vectors. It is an advancement in NLP that has improved the ability of computers to understand text-based content in a better way. It is considered one of the most significant breakthroughs of deep learning for solving challenging natural language processing problems. In this approach, words and documents are represented in the form of numeric vectors, allowing similar words to have similar vector representations. The extracted features are fed into a machine learning model so as to work with text data and preserve the semantic and syntactic information. This information, once received in its converted form, is used by NLP algorithms that easily digest these learned representations and process textual information.
What is the term thought vector in natural language processing? Thought vector is a term popularized by Geoffrey Hinton, the prominent deep learning researcher now at Google, which is using vectors based on natural language to improve its search results. A thought vector is like a word vector, which is typically a vector of 300 to 500 numbers that represent a word. A word vector represents a word's meaning as it relates to other words, its context, with a single column of numbers. That is, the word is embedded in a vector space using a shallow neural network like Word2Vec, which learns to generate the word's context through repeated guesses.
How deep learning works? Deep learning programs have multiple layers of interconnected nodes, with each layer building upon the last to refine and optimize predictions and classifications. Deep learning performs nonlinear transformations to its input and uses what it learns to create a statistical model as output. Iterations continue until the output has reached an acceptable level of accuracy. The number of processing layers through which data must pass is what inspired the label deep.
Breakout is the video game where a board moves along the bottom of the screen, returning a ball that will destroy the bricks at the top of the screen. The agent must learn to control the board by moving left and right, returning the ball and removing all the bricks. With reinforcement learning, we could try to make an agent that beats human-level performance in this game, given only raw pixels from the screen as an input, in order to maximize the score.
So this is the resulting video of our agent play. As you can see, our agent is doing pretty well with the ball moving at a low speed, and is also capable of adjusting the movements of the paddle as the ball speed increases when it hits more distant layers of bricks. The most wonderful part of all this is to see how the agent digs a tunnel around the side of the wall, allowing the ball to be sent around the back to destroy a large number of bricks, which in the original paper is considered to be the optimal strategy. So that's all for this video. Hope you managed to achieve good score in Breakout with the help of reinforcement learning. Please let me know in the comments whether you managed to destroy all the bricks. The learning process is really time consuming, but with proper hyperparameters and powerful GPUs, it's quite possible to get good results within 10 to 12 hours of training. Hope you liked this video, and I wish you good luck in reinforcement learning. Goodbye.
What is deep Q-learning? Deep Q-learning is a reinforcement learning technique that combines Q-learning, an algorithm for learning optimal actions in an environment, with deep neural networks. It aims to enable agents to learn optimal actions in complex, high-dimensional environments. By using a neural network to approximate the Q function, which estimates the expected cumulative reward for each action in a given state, deep Q-learning can handle environments with large state spaces. The network is updated iteratively through episodes, using a combination of exploration and exploitation strategies.
Computer vision is a field of artificial intelligence, AI, that enables computers and systems to derive meaningful information from digital images, videos, and other visual inputs and take actions or make recommendations based on that information. If AI enables computers to think, computer vision enables them to see, observe, and understand.
There are other tasks as well by computer vision, like sketch simplification, from drawing to vector graphic, image to image translation, video sequence prediction, deep stereo 2D to 3D image conversion, image generation used for architecture. These neural networks are learning what the visual world looks like.
It goes beyond image processing, which can remove noise or blur and identify objects based on size, color, or location. Instead, computer vision can also interpret the scene, identifying objects like pedestrians and traffic signs. More specifically, computer vision techniques can identify, track, measure, detect, and classify objects in images and video. Let's see a few of these in action. First, we'll look at how computer vision identifies objects based on motion. This includes very basic techniques like image subtraction, or more advanced algorithms like optical flow, taking into account groups of pixels rather than individual pixels. Next, you can see how computer vision is used for object tracking. Examples include point trackers for robust face tracking, or multi-object tracking for objects that are obstructed. Camera calibration allows you to remove lens distortion, measure an object's real-world size, or estimate distance from the camera. Next, feature detection, extraction, and matching allows you to find an object in a cluttered scene. Here, I'm able to detect and follow the object around, even if it changes size or orientation. You can use machine learning and deep learning techniques to identify or classify objects in a scene. For example, you can train a model to identify images of French fries or sushi. You can do all of these computer vision techniques in 3D using point cloud processing and stereo vision, which is a growing research area for autonomous vehicles and robotics. The idea involves capturing individual points in space and mapping them to a real-world scene. Hopefully, you now have a sense of what you can do with computer vision and what the term means.
You're absolutely right. Computer vision goes far beyond object detection and classification. These additional tasks showcase the true depth and creativity of machine learning applied to sight. Sketch simplification. Imagine turning a messy doodle into a clean, polished diagram. Neural networks can analyze and refine sketches, capturing their essence while removing clutter. Perfect for architecture or product design. From drawing to vector graphic. Ever wish you could instantly convert your hand-drawn masterpiece into a crisp vector graphic? Deep learning can now bridge that gap, translating your artistic strokes into precise digital vectors for seamless editing and scaling. Image-to-image translation. Video sequence as a magical paintbrush. Peeking into the future. Neural networks can translate one image style into another, analyze video sequences and predict what might happen next. Watercolor painting, helping robots anticipate a black and white picture into a high-driving cars, navigate traffic, or even generate realistic video extensions. Deep stereo 2D to 3D image conversion. Breathe life into flat images. Neural networks can extract depth information from 2D pictures, networks continue to learn 3D models. We can expect even more mind-blowing applications or medical applications between human image generation for architecture. From blueprints to breathtaking visualizations, deep learning can help architects bring their ideas to life. Neural networks can generate realistic building concepts, explore variations, and even analyze existing structures for potential improvements. These examples illustrate how computer vision isn't just about recognizing things. It's about understanding and interacting with the visual world in fascinating ways.
Pandora's box of mind-bending computer vision tasks. Let's dive deeper into these marvels. In art and creativity, album covers. Forget Photoshop battles. AI is now generating cover art that rivals human imagination, matching musical styles and creating visually stunning concepts. Fine art. Deep learning brushes paint across the canvas, mimicking artistic styles from Van Gogh to abstract expressionism, pushing the boundaries of creative expression. Plug-and-play generative networks. These democratize AI art creation, allowing anyone to input specific parameters and generate unique images. Think personalized portraits or landscapes born from imagination. Realistic faces. Imagine creating hyper-realistic portraits that could fool even the most discerning eye. Neural networks are crafting faces so lifelike they blur the lines between real and simulated.
Computer vision task beyond the still image lipnet. No need for audio. Deep learning can read lips with uncanny accuracy, translating spoken words into text, aiding communication for the hearing impaired, or even understanding silent movie dialogue. Visual concept to pixel magic. Think of it as a visual translator. AI can take abstract ideas like courage or tranquility and manifest them into pixelated landscapes or character designs, bridging the gap between imagination and visual representation. Cursive handwriting AI. From elegant quill-style penmanship to playful bubble letters, AI can now generate personalized handwriting fonts, adding a touch of individuality to digital communication. Inceptionism. Ever wondered what goes on inside a neural network's dreams? Inceptionism lets us visualize what an AI has learned, creating psychedelic distortions of images that offer a glimpse into the machine's understanding of the world.
In terms of videorama, video stabilization, shaky handheld footage, AI can smooth it out, transforming shaky amateur recordings into professional-looking videos. Video super resolution, upscale low-quality videos to pristine clarity, breathing new life into old footage, or restoring damaged films. Action recognition and sports highlights. AI can automatically detect and segment sports highlights, making it easier to find those jaw-dropping dunks or game-winning goals. Video style transfer. Apply iconic artistic styles like Van Gogh's swirling brush strokes or Rembrandt's chiaroscuro lighting to your videos, adding a touch of artistic flair. These examples showcase the sheer breadth and limitless potential of computer vision. From artistic expression to real-world applications, AI is changing the way we see and interact with the world around us. As these technologies evolve, prepare to be dazzled by even more amazing feats of visual perception and manipulation. Speech enhancement. Cleaning up noisy recordings, making communication clearer, and boosting audio quality in everything from phone calls to music concerts. Audio to video synchronization. Aligning audio tracks with video perfectly, ensuring lip-syncing perfection and smooth multimedia experiences. Deep learning in audio processing is more than just cool tricks. It's opening doors to new communication channels, enhancing accessibility, and unlocking deeper insights into the world around us, all through the power of sound. The future of audio promises to be as captivating as it sounds.
Syntax parsing, in the context of deep learning and NLP, involves analyzing the grammatical structure and relationships between words in a sentence. Imagine it like dissecting a sentence to understand how its parts, words, phrases, connect and build meaning. It's like figuring out the sentence's wiring diagram, revealing the rules and relationships that govern how words work together. Syntax parsing is a crucial skill for NLP models, allowing them to move beyond surface-level understanding and truly grasp the intricate tapestry of language. As deep learning techniques evolve, syntax parsing will become even more sophisticated, paving the way for even more natural and nuanced communication between humans and machines.
Training the RNN for text prediction. Feeding characters. The RNN is presented with text one character at a time. It's like showing a child letters sequentially to teach them how words are formed. Predicting the next letter. The RNN, like a language learner, tries to guess what letter comes next based on what it's seen so far. It assigns probabilities to each possible letter, forming an educated guess. Evaluating accuracy. The network's prediction is compared with the actual next letter in the text. If it's correct, great. If not, it's time for feedback. Backpropagation. Learning from mistakes. The error between the prediction and the correct letter is calculated and backpropagated through the network. This means adjusting the RNN's internal weights, like tweaking a recipe to get the flavors right. Boosting confidence. Dampening distractions. The weights are adjusted to increase the confidence likelihood of predicting the correct letter next time, while decreasing the confidence of incorrect letters. It's like reinforcing good habits and discouraging mistakes. Repeat and refine. This process is repeated for every character in the training text, countless times. The RNN gradually learns patterns and relationships between letters, building a language model in its neural connections.
Neural machine translation, NMT, is a game changer in the world of machine translation. offering significantly more nuanced and accurate translations than traditional methods. It's like bridging language barriers with the power of deep learning. NMT is a powerful technology revolutionizing machine translation. As research and development advance, NMT accuracy and accessibility will continue to improve, blurring the lines between human and machine language skills. We can expect even more efficient and nuanced translations in the future, bringing cultures and communities closer together through the power of AI.
Neural conversational models, NCMs, are AI systems that aim to hold natural and engaging conversations with humans, akin to how we chat with friends. They leverage the power of deep learning to understand the context, intent, and flow of a conversation, allowing them to respond in a coherent and relevant way.
Breast cancer diagnosis using deep learning is a hopeful advance. Deep learning is revolutionizing the field of medicine, and breast cancer diagnosis is one area where it's showing immense promise. The potential of deep learning in breast cancer diagnosis is immense. It offers a transformative opportunity for earlier detection, more accurate diagnosis, and personalized treatment, ultimately leading to improved patient outcome. Remember, this is a rapidly evolving field. Stay informed about the latest advancements and ethical considerations as deep learning continues to shape the future of breast cancer diagnosis and healthcare.
Deep learning plays a crucial role in reducing data center energy consumption by up to 40% through advanced cooling optimization. Data centers consume vast amounts of energy, with cooling accounting for up to 40% of that total. Traditional cooling methods rely on over-provisioning, constantly running at high capacity to ensure servers never overheat, even during peak loads. This leads to significant energy waste. The solution to the problem is that deep learning algorithms analyze historical data patterns, server workload, and environmental factors like temperature and humidity. This allows them to predict cooling demands with high accuracy, even for short-term fluctuations. Based on these predictions, the system dynamically adjusts cooling systems in real time. During low workloads, it can reduce fan speeds, power down inefficient cooling towers, or even utilize free air cooling when conditions permit. Some advanced systems use deep learning to optimize cooling at the individual server level, delivering targeted airflow only where needed. This hyper-localized approach further minimizes energy waste. Overall, deep learning offers a powerful and promising solution for optimizing data center cooling and significantly reducing energy consumption. By addressing the challenges and fostering collaborative efforts, this technology has the potential to reshape the energy footprint of the digital world and contribute to a more sustainable future.
Deep learning's poverty mapping remains a crucial tool for understanding and addressing global inequalities. Traditionally, relying on surveys and census data presented limitations in accuracy, coverage, and timeliness. Enter deep learning, injecting new life into poverty mapping with its ability to learn from vast amounts of data and unveil hidden patterns.
Cryptography is the study of techniques for secure communication in the presence of third parties called adversaries. Cryptographic algorithms are used to protect data from unauthorized access, use, disclosure, disruption, modification, or destruction. The use of deep learning in cryptography has both benefits and risks. The benefits include the potential to improve the security of cryptographic algorithms and to develop new ways to analyze and understand the security of existing algorithms. The risks include the possibility that deep learning could be used to break existing cryptographic algorithms. Overall, the use of deep learning in cryptography is a promising area of research with the potential to revolutionize the field. However, it is important to be aware of the risks associated with this technology. Most popular Google's products using deep learning, one of them is RankBrain. In few months, RankBrain has become the third most important signal contributing to the search result. Speech recognition, Google Assistant. 30% reduction in word error rate for English. Biggest single improvement in 20 years of speech research. Photo search, Google Photos. error rate of just 5%, which is as good as humans performing the same task. Also, superhuman performance in face recognition.
Some big companies offering deep learning tool for open source applications. What is quantum artificial intelligence? Quantum artificial intelligence, QAI, is a field that combines principles from quantum mechanics and artificial intelligence, AI, to enhance the capabilities of AI systems. It explores the potential of using quantum computing techniques to solve complex computational problems more efficiently than classical computers. What is neuromorphic computing? Neuromorphic computing is a method of computer engineering in which elements of a computer are modeled after systems in the human brain and nervous system. The term refers to the design of both hardware and software computing elements. Neuromorphic computing is sometimes referred to as neuromorphic engineering. Neuromorphic computing is an emerging field of science with no real-world applications yet. Various groups have research underway, including universities, the U.S., military, and technology companies, such as Intel Labs and IBM. Deep learning has injected a potent dose of AI into healthcare, revolutionizing everything from diagnosis to treatment. Like an X-ray for data, it scans images to spot tumors early, analyzes genomes to personalize medicine, and guides robots in surgery with superhuman precision. From chatbots offering mental health support to AI doctors predicting disease outbreaks, deep learning is transforming healthcare, one pixel at a time, promising a future where personalized medicine and preventative care become reality.
Medical imaging, disease detection, image-guided surgery, drug development, genetic analysis, drug target discovery, predictive medicine, analyzing electronic health records, prediction hospital readmissions, chatbots for mental health, medical robotics, drug dosage optimization.
The challenges of drug discovery and the role of AI developing new drugs is an arduous task. It has taken over a decade. The success rate had been only 10%. This is due to the complexity of biology and the countless chemical and protein combinations that need to be explored. However, discovering drugs to cure disease is an essential and admirable pursuit, and accelerating the process is crucial for drug developers. There are 3 stages of drug discovery: identifying the biology behind the disease, designing new molecules, small molecules, proteins, or antibodies, and finally, screening how these molecules interact. Fortunately, with the help of generative AI, with deep learning algorithms, every step of the drug discovery process is being transformed today. Drug discovery takes a leap into the future with deep learning. Forget slow lab work. AI sifts through massive molecular databases, predicting promising drug candidates that target diseases precisely. Imagine designing entirely new drugs, not just mimicking old ones. AI predicts protein structures, paving the way for potent, personalized treatments. This isn't science fiction. It's the dawn of a faster, more accurate, and cost-effective way to bring life-saving drugs to patients. Deep learning is unlocking the secrets of drug discovery, pushing the boundaries of medicine one molecule at a time. Deep learning aids in the discovery and development of innovative medicines in healthcare. The technology examines the patient's medical history and recommends the most appropriate treatment. Furthermore, this technology extracts information from patient symptoms and testing.
Deep learning is peering into the human body like never before, revolutionizing medical imaging. AI algorithms scan X-rays, MRIs, and CT scans with superhuman precision, spotting tumors earlier than ever. Gone are the days of blurry diagnoses. AI assistants now pinpoint abnormalities with remarkable accuracy, guiding doctors towards personalized treatment plans. This isn't just about sharper vision. It's about predicting future risks, streamlining workflows, and unlocking a new era of preventative medicine. From delicate robotic surgery guided by AI analysis to early diagnosis of neurological disorders, medical imaging powered by deep learning is transforming healthcare one pixel at a time, promising a future where technology illuminates the path to better health. Heart disease, cancer, and brain tumors are diagnosed using medical imaging procedures such as MRI scans, CT scans, and ECG. As a result, deep learning assists doctors in better analyzing diseases and providing the best treatment to patients.
Medical insurance fraud, a costly drain on the healthcare system, faces a formidable foe: deep learning. This advanced technology acts as a digital bloodhound, sniffing out suspicious claims hidden within mountains of data. Imagine an intricate web of connections, weaving together billing patterns, provider behavior, and patient records. Deep learning becomes the master cartographer, exposing anomalies and irregularities that traditional methods often miss. Like a tireless detective, deep learning analyzes historical data, the good, the bad, and the ugly, uncovering hidden patterns in legitimate and fraudulent claims. Billing inconsistencies, unusual frequency of certain procedures, or suspicious provider locations all flicker under deep learning's watchful eye. These patterns become red flags, alerting investigators to potential foul play. But deep learning isn't just reactive, it's proactive. By analyzing trends and identifying high-risk profiles, it predicts future fraud attempts before they take flight. Think of it as a crystal ball for insurance companies, allowing them to prevent fraudulent claims before they drain valuable resources. The benefits of deep learning. Number 1, accuracy and efficiency. Deep learning outperforms human analysis, minimizing false positives and negatives while churning through vast data sets at lightning speed. Number 2, scalability. No fraud scheme is too big. Deep learning handles mountains of data with ease, ensuring no suspicious claim slips through the cracks. And number 3, adaptability. Unlike static fraud detection methods, deep learning constantly learns and evolves, staying ahead of ever-changing criminal tactics. The challenges of drug discovery and the role of AI developing new drugs is an arduous task. It has taken over a decade. The success rate had been only 10%. This is due to the complexity of biology and the countless chemical and protein combinations that need to be explored. However, discovering drugs to cure disease is an essential and admirable pursuit, and accelerating the process is crucial for drug developers. There are 3 stages of drug discovery: identifying the biology behind the disease, designing new molecules, small molecules, proteins, or antibodies, and finally, screening how these molecules interact. Fortunately, with the help of generative AI, with deep learning algorithms, every step of the drug discovery process is being transformed today. Deep learning is a beacon of hope in the fight against medical insurance fraud. Its ability to analyze patterns, predict risks, and adapt to changing tactics makes it a powerful tool for protecting the integrity of the healthcare system. As this technology continues to evolve, we can expect a future where fraudulent claims are exposed with remarkable accuracy, paving the way for a more transparent and just healthcare landscape.
Ever pondered about what Alzheimer's disease is and how it affects people's lives? Alzheimer's is a progressive brain disorder that slowly destroys memory and thinking skills, often making simple tasks challenging. It's not just about forgetting where you put your keys. It's about losing the ability to remember cherished family moments, to make decisions, even to carry on a conversation. Globally, it is a significant health issue with millions of people affected. The real kicker is the disease's stealthy nature. It often goes unrecognized until it's well advanced. Early detection is crucial as it allows for interventions that can slow the disease and improve quality of life.
Recognizing the symptoms of Alzheimer's at an early stage can change the game. But how can we achieve that?
Enter deep learning, a subset of artificial intelligence that mimics the workings of the human brain in processing data. This powerful tool deciphers complex patterns in large data sets, much like how our brains recognize patterns in our daily lives. In healthcare, deep learning assists in disease detection by analyzing a wealth of patient data. It can sift through layers of information, pinpointing subtle changes that might elude the human eye. From predicting glucose metabolism to unlocking the secrets of proteins, deep learning is revolutionizing our understanding of health and disease. Deep learning brings a promising approach to early detection. But what's the latest in this area? Recent developments have seen an innovative use of deep learning in detecting early-onset Alzheimer's. In an intriguing twist, Twitter's vast data pool has been used not just for marketing insights, but also for medical purposes. The charity White Swan has leveraged this data to detect early signs of Alzheimer's in children. By analyzing patterns in user interactions, they have been able to identify potential early indicators of this disease. This is a groundbreaking step in the intersection of technology and healthcare, demonstrating how our digital footprints can be used for more than just advertising. Deep learning could potentially revolutionize the early detection of Alzheimer's, offering hope to many. So, the intersection of Alzheimer's disease and deep learning is an exciting field with immense potential. We've delved into the nature of Alzheimer's, a complex neurological condition that requires early detection for effective management. We've also explored the transformative role of deep learning, a subset of machine learning that can sift through and make sense of vast amounts of data, including markers for diseases like Alzheimer's. The latest advances, such as the potential use of Twitter data for early Alzheimer's detection, illustrate the boundless possibilities in this sphere. With the advances in deep learning, the future of early Alzheimer's detection seems brighter. Stay tuned for more insights into the world of medical technology.
Imagine a world where your health inquiries are answered promptly, 24/7, with no hold music or waiting times. Welcome to the era of healthcare chatbots. In the past 5 years, there's been a seismic shift in the way we interact with technology, particularly in the healthcare industry. A startling fact that underscores this shift is that, by the end of 2023, the use of chatbots in healthcare has increased by a staggering 70%. So why this sudden surge? The healthcare industry, despite its noble intentions, is fraught with inefficiencies. Patients often face long wait times for appointments, there's a lack of personalized care, and the communication gap between patients and healthcare providers is vast. Enter chatbots. These AI-powered virtual assistants are designed to streamline processes and eliminate the bottlenecks that plague the healthcare sector. They are capable of scheduling appointments, providing medication reminders, and even offering preliminary diagnoses based on symptoms input by patients. Chatbots are revolutionizing healthcare by providing real-time assistance, reducing workload on healthcare professionals, and most importantly, enhancing patient engagement and experience. They fill the communication void, ensuring patients feel heard, understood, and cared for. But how do chatbots achieve all this? Through the power of artificial intelligence and machine learning. These technologies enable chatbots to learn from each interaction, continually improving their responses and offering more accurate information over time. But the potential of chatbots extends far beyond these applications. Researchers are exploring their use in mental health support, chronic disease management, and even in educating patients about complex medical conditions. The rise of chatbots in healthcare is not a trend. It's a testament to the industry's commitment to leveraging technology to improve patient care. As we move forward into 2024 and beyond, the role of chatbots in healthcare will only continue to expand. The future of healthcare is here, and it's conversational. We encourage you to delve deeper into the world of chatbots, understand their capabilities, and explore how they can reshape the healthcare landscape. To paraphrase a famous saying, to predict the future of healthcare, one must understand chatbots. So, stay curious, keep learning, and remember, the next time you have a health query, You might just be speaking to a chatbot, and that's a good thing.
Deep learning is rewriting the script for prescription audits, transforming them from tedious, error-prone processes into efficient, insightful guardians of healthcare integrity. Imagine AI meticulously scanning for mountains of prescription data, pinpointing potential errors and discrepancies with laser-like precision. Gone are the days of manual drudgery. Deep learning acts as a tireless watchdog, sniffing out improper diagnoses and treatments by analyzing patient records and medication history. AI flags prescriptions that don't align with diagnoses or established treatment guidelines. Secondly, dosage anomalies. Excessively high or low dosages trigger an alarm, prompting further investigation into potential abuse or medication interactions. Thirdly, fraudulent billing. Patterns in prescribing or billing that deviate from typical practices raise red flags, helping identify illegal activities.
Deep learning is ushering in a new era of precision and insight in prescription audits. It isn't just about uncovering errors. It's about safeguarding patient well-being, optimizing healthcare practices, and building a more efficient and transparent system. As this technology evolves, we can expect a future where medication usage is monitored and optimized with unparalleled accuracy, ensuring quality care for all. Deep learning is peeling back the layers of mental health, offering exciting prospects for understanding and supporting those in need. Imagine AI analyzing vast data sets of brain scans, clinical notes, and patient behaviors, uncovering hidden patterns and insights into complex mental conditions. This isn't mind reading. It's a data-driven approach to unlock the mysteries of the mind, potentially improving diagnosis, predicting risks, and even personalizing treatment. From tracking early signs of depression to optimizing therapy programs, deep learning promises a future where mental health receives the precision and understanding it deserves.
Is deep learning the future? The answer is yes. Deep learning in healthcare holds great potential for streamlining complex data analysis, improving diagnoses, and shifting the benchmarks of patient care in a cost-efficient way. As more medical professionals recognize its value, deep learning is making inroads in the healthcare industry. Collaboration with industry experts and specialists will further enhance the capabilities of this technology, which must remain adaptable to remain relevant to the medical profession.